Okay, so how many atoms are there in a teaspoon of water? Is it a million, which is a huge number, a billion, which is an absolutely colossal number, a trillion, which is just getting silly, or is it a million trillions? Imagine how big a trillion is and take a million of those. Wow, that is a stupidly big number. Or is it this one I just put in as a joke? A million trillion. Nothing could ever be that big. What is the answer? Of course, it is a million trillion. Only half the class knows how many atoms are in a teaspoon of water. There is one number in chemistry class that gives you a hint. Does anyone know the secret constant you're supposed to memorize? Yeah. A mole. Yeah, a mole is not a small furry animal in this case, but is a large quantity of atoms, and it's about 10 to the 23, 10 to the 24 atoms. And if you have like 10 grams of something, that'll be like 1 mole. The number on the periodic table tells you how many grams are in a mole. So like carbon is 18, so there's 18 grams in a mole. I probably got that wrong. Someone correct me. Someone who's good at chemistry. Is that approximately correct? No one's really upset, so maybe it's not horribly wrong. I was never very good at chemistry. But 10 to the 24, this is a good number to remember. In a single teaspoon of water, there are 10 to the 24 atoms. Yes?
Dr. Nika,
Yeah.
like I got spoons at home, and some of my
Yeah.
teaspoons are a little different sizes.
Yeah.
Did you work that into your?
Well, I was just approximately, So I was just going for the exponent part. If you have a bigger or smaller teaspoon, you'll multiply by 5, or by 7, or by 2, or something.
It's actually more like
Yeah.
1.05.
Yeah. Well, it depends how big.
Like
yeah. Exactly. Yeah. Exactly. So it depends how big your
to
teaspoon
the nearest
is.
order of magnitude.
I was going actually not even the nearest order of magnitude. The nearest words. All of these have to be a whole number of words. So like I couldn't make 10 to the 23, for example. I could only make 10 to the 24.
And you could work out how many were hydrogens and how many were oxygens.
You could do that too. Well,
you could do that too.
Oh yes, okay, that's true. I said atoms and molecules. I guess there would be 3 times as many atoms as there are molecules, but it's all the same. Maybe I should have said molecules.
Maybe.
I will say the reason I like the word atom is a proper probability word. When you take a graduate level probability and you do research in probability, you might be talking to someone and they say, this probability distribution has an atom. That is something they might say. An atom is what you guys all know on probability mass function. It is a point that has a non-zero probability. That is called an atom. So for example, the binomial distribution with n things has n atoms.
That is so confusing.
Yes. And why do we say this? Why do we say this? Well, because the other type of distribution that you know about, the ones with probability density functions, they have no atoms. They're this continuous mess. Every single individual point is probability 0. And so we use this word atom to sort of distinguish them. And that is actually exactly what we're going to do today. So the reason I did this as a warm-up question, just as a teaspoon of water is actually secretly under the hood, if you open the universe and look at what's going on, is actually a million trillion atoms, we're going to see that if you have a dice with enough sides, so this is one with 100, if you put enough sides on the dice, it starts to behave not like a collection of 100 different atoms, but like a collection of something continuous, like a teaspoon of water. So just as a teaspoon of water is made of lots of little atoms, so too are continuous probability distributions made of things that are many atoms, or they can be made of things that are many atoms. So that's what we're going to see. Okay, questions or comments about the warm-up? So once again, we're looking at this 100-sided dice that I brought in last time, and we're asking what happens as you add more and more sides to the dice. And I have a little bit of a Desmos thing to show you. And what I've done here is I have made, let's set n equal 20. I've made a little demonstration of my 20-sided dice. I have put the atoms that represent these little events, the probability it's equal to 1, the probability it's equal to 2, I have put them on the x-axis as little dots. So it's really reminding us of atoms. So this little picture is supposed to represent a 20-sided dice. A 20-sided dice, it could be 1, or it could be 2, or it could be 3, and each of them have probability 1 over 20. And so if you look at the area of these dots, each dot is area 1 over 20. It has been cooked up that way. Actually, I have a little slider. I can make it a little zoomed in or not. I think the slider is called, what is the slider called? C. I make them a little bigger or smaller. Let's make them a little bit bigger. Otherwise, we're going to have trouble seeing them. Let's make them a bit bigger. Okay, I think like that's quite good. So there's a 20-sided dice. Ooh, and Desmos has smooshed it a little bit for us. Well, okay, you can use your imagination and pretend they're circles. But there's 20 atoms. You should imagine 20 atoms that make up our 20-sided dice. That's very nice. The question we're going to ask is what happens as you add more and more sides. So you go from a 20-sided dice to a 36-sided dice, which is one of the ones I have over here. This was the dreaded 36-sided dice. Let's see what happens. And the nice thing is we just have to take our slider and make it bigger. So let's make it a bit bigger. So two things are happening as we make it bigger. You'll notice it's getting longer, but something is happening to the circles. Something interesting is happening to the circles as you make it longer. And you remember, this is the so-called uniform distribution. Uniform meaning every individual thing has the same probability. And if everything has the same probability, something must happen to the individual probabilities. I have a mathematized question for you to tell me what is happening to the individual probabilities. That is next on our agenda. P equals something. So here is the mathematized. dn stands for a dice roll with n sides. So let dn be the random variable for a dice roll with n sides. So it's 1 or 2 or 3 all the way up to n. Fill in the blank with what happens to the probabilities as n gets large. As n gets large, the value of the probability, for example, the probability dn equals 7, it gets closer and closer to blank. It's getting closer and closer to what? So not only do you need to maybe know the formula, but you kind of need to intuit what happens. And to make it extra provocative for you here, I'm going to hit play and animate this thing, and you can watch what happens to these probabilities as n is getting bigger and bigger. And then the animation will restart, and we'll go back to a one-sided dice, and then we'll have a more and more sided dice. Okay, I will let you think for a minute while we do this. All right, 10 seconds to go. Those of you taking calculus might realize that secretly this closer and closer thing is actually a limit. I'm talking about what is the limit of this thing. Who's taking calculus this year? Math 1200, almost everybody. Who's heard of a limit? Who's heard of a limit? Okay, most people. Very good. So we're really doing a limit. I'm just not saying limit because we don't have to get into the gory details. We're just doing the fun side of limits, not the hard, scary side. Okay. What did people say? Let's find out. It's getting closer and closer to 38 people said 0 out of 41 people, and that is absolutely the right answer. So as we add more and more sides to the dice, this is the thing to realize is the individual probabilities get closer and closer to 0. This is the first most important thing you must know about these kinds of things, is that in a lot of situations, especially when a discrete is going to a continuous, the individual probabilities, they get closer and closer to 0. Let's write that down. This is something worth jumping up and down and making sure to get correct. Let's do this. Okay. So when, oh boy, that's the wrong pen. Okay, let's try again. When a discrete random variable, e.g. a dice roll, converges to a continuous random variable, the individual probabilities usually go to 0. Let's just say, let's say if individually go to 0, and I'll put a star, and I'll say terms and conditions apply. Individually go to 0. So this is almost always true, but sometimes weird stuff happens. So just, yeah, be careful. Anything in this class, it will for sure go to 0 if you're converging discrete to continuous. But mathematically speaking, if I don't warn you, the math police will come arrest me. Okay, individually go to 0. Okay, so the probability mass function, the probability that dn equals 7, this goes to 0. We put arrow 0, and you cannot look at the individual probabilities. The individual probabilities will be not informative because they just go to 0. So it doesn't tell you what is the probability density function of the thing it's converging to. Oh, it's just going to 0, so we don't know. So the solution, and this is why this is an important thing to understand, the solution is you must not look at the probability mass function. It is not going to give you the information. So we're going to look at something else instead. We're going to look at something else. Instead. When you're doing this kind of convergence, you must look at the right thing, or you will not see the convergence. And the something else is something that both discrete and continuous random variables they both have this thing. Continuous random variables have it. And it's something we've mentioned in the class before, although we didn't make too big out of a deal of it. But it is extremely important for this reason. It's the thing that is the linking thing that both discrete and continuous do, and therefore you can use it to see one getting closer to the other. Does anyone have a guess? What is the thing I'm talking about here? Not the probability mass function, it's something else. Any guesses? Let me give you a hint. For continuous random variables, we had lowercase f, which was the probability density function, the dreaded PDF. And then there was something called capital F. There was also a capital F of x, which was something else. Does anyone remember what is capital F? Yeah, the cumulative. Very good. See, you do know it. I knew. The cumulative distribution function. And then, this is much fuss about what is the letter for this in R, right? In R, for the F, you do the D norm, or the D binom. This is the D norm, e.g. And then the cumulative is called the P norm. And one is the density function. One's an honest-to-goodness probability. The density function is the f of x. The cumulative distribution function is capital F of x, is the probability that the random variable you're talking about, x, is less than or equal to x. And by doing a less than or equal to, then we have a chance the continuous random variable is converging to an honest number. This p won't be 0. It'll be some actual number. And that's the area sort of up to the point x. So this is an important thing to remember. Maybe you have some picture like this. Ooh, here, I'll draw the one from the midterm. That's a good one. All right, there we go. And then you have f of x is the area up to some point x. And someone could say, for example, they could ask a question like, for what value of x is f of x equal to 1/3? For what value, that could be a valid question, of x is f of x equal to 1/3? And then you would find the area up to this point x. Okay, so that's the cumulative. And the point is that the discrete and the continuous both have cumulatives, and those cumulative functions can actually converge. So we're going to look now at the cumulative distribution function for the dice rolls and see what happens. Okay. Any questions or comments about the cumulative before I start the example? Something? Okay, let's do it. And so here is my mathematize, and now I'm going to p less than or equal to something. So same kind of situation as before. Let dn be the random variable for the dice roll with n sides, just like before. Find out what happens to the probabilities as n get large. But now, instead of asking about the probability dn equals 7, I'm going to ask for the probability that dn is less than or equal to 7. And once again, I'm going to draw the picture in Desmos, in my other Chrome thing. Where did it go? Dice rolls. Okay. So this was the thing. And now I'm going to draw this. Okay, this is my, this is the cumulative distribution function. Let me make this bit smaller and a little more zoomed in. Let's maybe make this y less than or equal to 1. And we'll start at negative 0.1. And we'll go up to 1.1. So hopefully we have a nice view. Okay, and now you see I made the things way too big. So I have this little slider. Do. Put these back down where they belong. Okay, so these little blue spikes over here, these are the little atoms, like the representation before. And now I have drawn the cumulative distribution function as this step function. This is the cumulative distribution function for the dice roll. What is the probability that the dice roll is less than or equal to 5? It is, in this picture, is a little bit over 0.4. How many sides are on my dice here? Let's look at that. Oh, it's a 12-sided dice. Why don't we go to a 10-sided dice? That'll be a little bit easier to answer. So if we ask a question like, what is the probability that it's less than or equal to 5? It's 0.5. Perfect. So this step function, it jumps up whenever we hit an integer, and those jumps are the atoms over here. So this thing is the cumulative, and these are the atoms over here. I think we've drawn this kind of cumulative step function before in the course. Everyone okay with this picture for the step function is the cumulative? Yes, is there an issue?
Professor, so I like the y-axis being respawned, but
Yeah.
the fact that it still can be negative.
What can be negative?
Why are those things extending below the line?
These things?
Yeah.
Oh, yes. Okay, so these are like supposed to be representations of little masses, right? Like we saw before. So it's kind of a funny, you would never, this one doesn't have a name. This is called the cumulative. There's also the probability mass function. And then this is Professor Nika's dopey cartoon of trying to make it like real life by having 10 masses to make it look like atoms. They're little circles. Yeah, you think they should be. They're supposed to be circles, but because the axis is so compressed, they come out as non-circles. Hold on, I know what'll fix you. Let's divide. We'll change the formula for the area of an ellipse. We'll make them more circular. There we go, and then we'll shrink them. There you go. Better? You see, they're 10 little masses. They're like little balls, and they have a little mass. And each of them has a mass of 1/10 of a gram. And then as we add more of them, they're going to get lighter and lighter, as we saw. Yes. Okay. Good. I'm glad we cleared that up.
Right on that zero axis.
Yeah, I could have drawn them anywhere. I should have drawn them in somewhere else. These guys exist on the number line, whereas everything else exists sort of on an actual graph. Yes. Okay. Good. I'm glad we clarified because that was the weakest part of the drawing. Okay. Any other questions or comments? Okay. So now we're going to do the same thing as before. We're going to ask what happens to the cumulative distribution function as n gets large. So we see what happens to n gets large as we do this. We add more and more masses. The mass of each one goes down. What happens to this thing? Okay, and let me set the axis again a little bit larger so we can see. But let's go all the way up to 75, let's say. So there we go. This is the beginning, 0 to 10. And then as we get bigger and bigger, let's see what happens. Here's the animation. Okay, so that's what's happening. You know what's happening with the masses. We talked about that. Every individual mass is going to 0. What does that mean for the cumulative distribution function? Okay, and I'll let you answer the question over here in Mathematize. What is the probability? The probability dn is less than or equal to 7 gets closer and closer to blank. Okay, 30 people have already answered because I left it open, so maybe it's easy. I don't know. Okay. Okay, I'll leave this picture up. And I will give you another minute to think what you can from the picture. Let's see what people said. Okay, let me grab this and put this here for future use, unless Google doesn't like me today. Okay, let's see. Let's just see what people said. Okay. Reveal counts. Let's see. It's getting closer and closer to. Oh, this is great. We got a nice split. 22 people said 0. 15 people said 1. Some people said it does not get close to any number. So we're a little bit split here. What are we talking about? We're talking about the value of the function at 7. So maybe to help you understand what's going on, right? It's hard to maybe look at this thing. Let's draw a line at x equals 7. And then that will help us understand what's going on. Let's draw the line x equals 7. There's a nice vertical red line at x equals 7. We're talking about the value of the function at x equals 7. And over here, when n equals 5, then if you roll a 5-sided dice, what is the probability that the 5-sided dice is less than or equal to 7? It's 100%. But then for a 14-sided dice, okay, no, I don't want to change x. I want to change n. 14-sided dice, what is the probability that a 14-sided dice is less than or equal to 7? That's 50%. What about a 21-sided dice? A 21-sided dice. What is the probability that a 21-sided dice is less than or equal to 7? Okay, I look at the thing over here, and it's right around a third, 33%. Okay, what about a 28-sided dice? This one is a quarter. Okay, so now you know how to read the function. We're reading off values of the function, and we're saying, are those values getting close to something, and if so, what? And now, okay, we had a split. What was the split before? The split was, most people said 0. 22 out of 38 people said 0. 15 people said 1. What is the correct answer? The correct answer is 0. It is 0. And so, in fact, you can see if you fix any line, then as we get larger and larger, you see they're shrinking down. The values at any particular value are shrinking down. For any fixed x-axis, any fixed x value, the value of the function is getting closer and closer to the line. If I maybe even make it more extreme, let's go up not up to a 100-sided dice, but a 1,000-sided dice, and then you'll really see it shrinking down over here. The function is shrinking down over here. The probability is getting closer and closer to 0. And in fact, this whole cumulative distribution function seems to be getting closer and closer to everyone's favorite function called the 0 function. And this is a real problem. This is a real thorn in our side. And we're going to write this down as our next little moral. So sometimes, the cumulative distribution function is, I'm going to call it, this is a fun word I read once, effervescing away. It is sort of like, the probability is sort of disappearing. We had probability 1, and then, we're kind of like, it's kind of getting spread out, and there's none left. So the f of dn of x, that goes to 0 for any fixed x value. So even though it starts at 1, the cumulative distribution function, not only is the individual probabilities converging to 0, like we had before, the probability mass function, but the cumulative distribution function is also going to 0. And when this happens, this means the dice rolls don't converge to anything. This means the dn's are not converging. They're not converging. They are escaping. Okay. Again, just like before, the reason this is an important lesson is because when this happens, you have to do something. We must do something to contain it. We must do something to contain it. So the dn's on their own, they will not converge to anything. They kind of, as you add more and more sides to the dice, and you roll the dice, you're just going to get bigger and bigger numbers. It's never going to settle down into something nice. We have to do something to contain this random variable. We have to put it in a pen so it cannot escape. We have to do something. I think I have a mathematizer. You write down, you tell me your zany ideas. How do we corral this random variable? Let's see, do I have that? Ideas, yes, tell me your ideas. It seems to evaporate as n gets larger and larger. Do you have any ideas on how we could contain it? I'll let you think for a minute. Tell me your best ideas. Maybe your best idea is, I have no idea, it's Friday morning, man. That would be a totally fine idea. But do your best thinking for 1 minute, and we'll see where we get. How could we contain the dice roll so that it actually converges to something, gets closer and closer to something? Just a couple seconds left. What did people say? What are your ideas? DNE. Okay, let's see. Lots of people don't know. Bound it. That's exactly what we want to do. We want to do something that we're going to hit this random variable with the algebra hammer to make sure it doesn't escape, right? Before, it's getting all crazy big. A 100-sided dice, you could roll 100. We don't want big numbers. We're gonna bound it, but how? This is a great idea. If you can answer how we're going to bound it, then that's what we're doing. I don't know. Okay, great. Give it a range. That's right. Not only like it is in a range, it's in the range 1 to n, and the problem is that n is getting bigger and bigger. So we want to not only give it a range, we want to make sure the range is not getting bigger and bigger. We want to make sure the range is some fixed amount. Okay? Restrict the domain. Yeah, same idea. Very good. Nope. Bound on x. Bound on x. Yes. Okay. Very good. So some people are getting at the idea. All right. Make it go in. Can you buy the class Muck Donald? I don't know who this Donald fellow is. Let's continue. Okay. Not sure. Setting the max value. So lots of people are on the right idea with the limit. Too hungover to think. Yes. That's always a problem when you're doing probability. Okay. Set the max value. Okay. So some people have the right kind of idea of what we want to do. How are we going to achieve it? And when I tell you, you're going to say, oh, that's so simple. We learned that in grade 4. So dn ranges from 1 or 2 or 3 all the way up to n. Actually, let me use curly brackets. Okay. How can I make it? I'm going to do something to dn, and then it's going to range inside some interval where the maximum number is 1. So it's not going to escape. It's always going to be less than or equal to 1. How do you take something that's between 1 and n and make it less than or equal to 1? Just divide it by n. dn over n. And dn over n will be either 1 over n, or 2 over n, or 3 over n, ... Or it could be, if you roll the highest number on the dice, it could even be equal to 1, but it will never be larger than 1. And by doing so, we have contained it. Instead of being this huge range that's getting bigger and bigger and sort of evaporating to nothing, we're containing it. We're shrinking it into some better range. Okay, and what does this look like? Once again, these are the dice rolls. Let's get rid of this. Let's fix a value, a reasonable value like 20. Let's move this back down to the 100-sided dice so we don't go crazy. This was the dice roll. Here it is 0 to 20, and where the x-axis kept getting bigger and bigger. But now I'm going to do the same thing not for d, but for something I called x. Let me put x up. X is equal to d over n. This is a new random variable. I took the old random variable and divided it by n. And here are the values it can take on, 0.05, 0.1, and so on. And here is, just like we had the blue dots on the x-axis for dn, now we have the blue dots on the x-axis. They're green dots. Those are the dots for xn. You see? And they're all between 0 and 1, because the random variable can never be larger than 1. Okay. So now we're cooking here, because it's always between 0 and 1. And so as we add more and more to n, right, the dice rolls themselves are going crazy. They're moving off to infinity. But what's happening to the xn's, dn divided by n? It's just getting more and more dense in there. You see that? You see that in here, in this little interval? We're getting more and more stuff, but it's not escaping. We're containing it. This is very exciting to me. Okay. Let's look now at the cumulative distribution function, because again, the individual probabilities are the same as the individual probabilities over there. They're all going to 0. But the thing that's exciting is the cumulative distribution function, which I call g. Okay, let's do a little zoom in here. And I'll make my x-axis go from negative 0.2 to 1.2. And I think, unfortunately, we're going to throw away the blues, because there's some crazy big thing over here. But there are my points. And there's my cumulative distribution function. All right, I immediately zoomed out to change this. Negative 0.2. And then we want the y-axis to also be going up to 1. Very similar kind of vibe. Okay, let's do that. Okay, so there's my atoms down here. This is my cumulative distribution function. What happens as n gets larger and larger? Make a prediction in your head. What happens to the points? What happens to this function as we add more and more? Truly, this is the magic. This is the magic happening here. Here we go. Okay, before the function was effervescing, they were spinning off to infinity. Here it's just getting more and more dense. we're sort of filling in the whole interval 0, 1. We're filling it in more and more densely with these tiny, tiny atoms. Each individual atom is getting smaller and smaller, but they're sort of becoming an infinity of atoms everywhere. And the cumulative distribution function, it's a step function, but what is it getting closer and closer to? It's getting closer and closer to a perfectly straight, honest-to-goodness line. So if we draw the function, we take the function y equals x. This function is not a perfect match to the step function, but the step function is getting closer and closer to it. And this is what convergence of random variables is. It is the cumulative distribution functions are converging. We have corralled the dice so that it converges to something. And let me write this down on the board. I think this is extremely exciting. OK, this one converges. So let xn equal dn over n. Then notice the cumulative distribution function, function for xn is converging. It becomes the function y equals x. Well, actually, it becomes a function either 0 or x or 1, depending on if x is less than 0, x is bigger than 1, or x is in the range over here. So it's this step function over here that is like this. And then it hits a maximum at 1. This is always between 0 and 1, the random variable. And so that's where all the action is happening. So this is converging. OK. All right, we did it. We made the dice converge. Now we can ask a question. Do we recognize this thing? Is this the cumulative distribution function, all right, CDF, of something? Is it? Is there a continuous random variable for which this is the cumulative distribution function? We haven't done a ton of cumulative distribution functions. What is something where the area kind of goes up at a constant rate? The slope here is 1. And so that you could say the area is increasing at a constant rate. Area increases at a constant rate. Once again, if you're taking calculus, you'll know all about these ideas of the interplay between rates and areas and things like that. Maybe if you're taking calculus, you're screaming at the screen right now in your mind. What is the density function? There's a very nice density function. It is this density function. Here's the axis, and here is the density function. It's the function that looks like this. The rectangle function of height 1 is I guess this is a square. I'll say rectangle / square density function on 0, 1. Okay, and why is that? If you take the area on any region up to some point x, what is the area of this region? Well, it's base times height. So the area up to y equals, or up to this x is exactly x. The area here is x, and that matches the formula over here where the area was x. So the cumulative distribution function that we're converging to is this rectangle or square-shaped area function. This could have been a good one for the midterm. It's a very, very simple one, and we promised you we'd have a lot of nice shapes like this. So what is the moral of the story? Putting it all together, dice rolls converge to this thing. Converge. And when they converge, you can say they're approximately equal. So the dice roll divided by n is approximately equal to whatever this random variable is, this guy. This thing has a name. It is sometimes called the continuous uniform random variable, the continuous uniform random variable. Okay, and sometimes people call this U. U is very nice. If you have a calculator and it has a rand button, and it gives you random numbers between 0 and 1, what it is giving you is this continuous uniform. And the nice thing about these approximations, if someone says dn over n is approximately u, you can do things like you can say dn is approximately n times u. And so if you want to roll a 6-sided dice, you can press the uniform button on your calculator, get a uniform number, and then multiply it by 6. That will be approximately a dice roll. And this works for any number of sizes. If you want to approximate a 100-sided dice, you get your calculator out, you press the U button, or the rand button, sometimes called rand, you multiply it by 100, that's like simulating a 100-sided dice roll. All right, very nice. Let me show you one other quick application here in the last few minutes. Let's do an application of finding the expected value. Finding the expected value. And so the nice thing about these things is these approximations, they can be incredibly useful because sometimes it's much simpler to do things with the u than it is to do things with the dn. Let me show you finding the expected value on both sides of this equation. So the expected value on this side is n times u, and that is n times the expected value of u. So you have to find the average value of this uniform guy. And the uniform guy, remember, is this little square density function going from 0 to 1 and of height 1. Now, if someone says, please find the expected value of this, there's two different attitudes you might have. One, you might panic because we've never seen an expected value for a continuous thing so far. But actually, in this case, it's quite easy. So if you sort of remember the core of what is an expected value, it's actually quite easy to do this. Does anyone know just immediately what is the expected value of this uniform based on the density? I can also remind you, it's the finding the center of mass is the other way to think about it. What would it be? Yeah, there's a question here. You're just stretching. You must be the hungover guy. No. Okay. All right. Yeah. It's exactly 0.5. Very, very good. It's exactly in the middle, 0.5. And if someone says, why is that? Well, look at by symmetry, right? Where is the midpoint, the center of mass of this thing? Half the mass is to the left of 0.5, half the mass is to the right of 0.5, and they're perfectly symmetric. So if you sort of have a pipe that is uniform, of course the center of mass has to be in the middle. It's 0.5. You could also check this with calculus. If you know calculus, then you would find the area of this times x, and you do the integral of x, and you would find the integral of x is something about a half. But in this case, it's very easy to see just by looking by symmetry. And therefore, the thing we're talking about here, this is n times 1/2. OK, easy, very easy to do. The expected value is n times 1/2. On the other hand, what is the expected value of a dice roll? Well, let's do that, of dn. And by our formulas, you have to sum over all the possible values times the x value. So it's the sum, remember, the sum over all possible x values, and you do x times the probability that dn equals x. And in this case, this is the sum of, it could be 1 or 2 or 3. I'm going to call the numbers j. j going from 1 to n, you do j, and the probability is 1 over n. And so you would end up with 1 over n times the sum from j equals 1 to n of j. Now you got to do this nasty sum. Oh my goodness gracious, how are we going to do this nasty sum? There's a famous story that when Gauss was a child in grade 2, that he was being very annoying. So his teacher said, please go add up the first 100 numbers, Gauss. That'll take you all day, ha ha ha. But then Gauss found an amazing trick, which is you write it out twice. So you do 1 over n, and then you do 1 plus 2 plus 3 plus dot 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 plus n. This is the answer we're looking for. And then you write it out again in reverse, n plus n minus 1 plus n minus 2 plus dot 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 plus 1. So here's little baby Gauss writing out the numbers 2 ways, and then you add these two together. So 2 times the answer is what I get if I do this plus this, and that is equal to 1 over n. 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is also n plus 1, and so on, all the way up to n plus 1. OK, so I have n plus 1 plus n plus 1 plus n plus 1 plus n plus 1 n times, and there's a 1 over n here. So n, adding up the same number n times and multiplying by 1 over n, these cancel out. So the final answer is just n plus 1. But of course, this is not we're not done. 2 times the answer is n plus 1, and therefore the answer is n plus 1 divided by 2. N plus 1 divided by 2. So there you go. That's the answer. Now we can compare the two answers and see, first of all, which one was easier? What was quicker? What was quicker and more intuitive? I think it was this one. Of course, you have to not be scared of continuous things, which as you develop more calculus skills, you'll get better and better at. But this one is real beastie if you don't know what to do. Of course, this is, in some sense, a beautiful formula. But you have to know the tricks, know how to do it, and there's no way around it. There's no way, you can't just look at this and know. Finally, let's compare the answers. This answer says the answer was n plus 1 over 2. This one, we just got n over 2. Where did the plus 1 go? Well, of course, it's not an exactly equal. It's an approximately equal. And these are, if we did it this other way, with the divided by n, we would have seen that the error between these two things is very small compared to how big it is, right? This is n over 2, like 1,000 divided by 2. This is 1,001 divided by 2. Very close numbers. So they're close, but not exactly equal. That's one application, finding the expected value. OK, I think I've said quite a lot of things here. This is a good place to pause if there's any questions. Any questions or comments? Yeah. Why is it n plus 1 plus n plus 1 plus n plus 1? So you add it up column by column. So you do 1 plus n is n plus 1. And then over here you do 2 plus n minus 1. What is 2 plus n minus 1? Well, you started at n, you went down by 1, and then you went up by 2. So you're at n plus 1. Why is it 1 plus 2 plus 3 plus 4? No, it's not a silly question yet. So the reason is because the dice roll, those are the values the dice roll can take, right? The dice could be 1 or 2 or 3. And when you do the expected value, you add up all the different values that it could take. So because it is a dice roll, and these are the sides of the dice, to find the average. It's true if it was a different random variable, if it was some like grid, or they had different probabilities, you wouldn't simply add them. You would have to do like whatever values it could be times their probabilities. But in this case, it's all the numbers 1 to n because they're simple dice rolls. Yeah, great question. All right, any other questions? OK, as a little bonus here, so if you're scared of these things, then treat this as bonus. Let's find the variance. So we did the expected value, but now things get really exciting. Let's find the variance. On the left-hand side, we're going to do the same thing again, and I'm going to skip some details here to fit this in. But on the left-hand side, you have to do the variance of the dn. And to find the variance of the dn, at some point you're going to need to find the expected value of dn squared. And the expected value of dn squared, again, using the formula of summing over all possible x values. This time you have to sum over x squared times the probability that dn equals x. And that will be the sum of the squares. So this will be 1 over n, 1 squared plus 2 squared plus 3 squared plus dot, 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 all the way up to n squared. And if you thought the last one was scary, this one's a real doozy. I don't actually have a nice, simple way to do this one. You have to, I don't know, this one's quite hard. This is hard. You can look it up, of course, but I would say this one is legitimately a hard problem. On the other side of the fold, let's find the expected value. Or actually, let's go directly to the variance. The variance of u. What is the variance of u? And the variance of u, remember, it's the expected value of u minus its average. And its average was really easy. That was a half. So it's the expected value of u minus 1/2 squared. What does u minus 1/2 look like? It's the density that is, now we've centered it. So if this is the x and the y axis, then centering it gives you this density function. This is the density function f. For u minus 1/2. I took the density function before and I shifted it over by 1/2, right? But before it was going from 0 to 1. Now it goes from negative 1/2 to positive 1/2. Negative 1/2 to positive 1/2. OK. How on earth am I going to find the expected value squared? OK, and this is why this part of the calculation is this is why this is a bonus question, because unfortunately, I think the only way to do this is to use a bit of calculus. So if you don't know calculus, there is no calculus on any of the exams or tests or anything like that. You do not need to know this calculus thing. But if you do know calculus, this is a nice, simple calculus equation. The expected value of this thing is equal to this integral from minus 1/2 to plus 1/2 of the function x squared dx. And if you are taking calculus class now, you will look at this and you'll say, hey man, that's the easiest integral in the whole world. If only that was the question on my calculus exam, I would be so happy. And in this situation, I believe the answer should be a third. But don't quote me on that. Let me not say it. Let me leave it as an exercise so I don't get it wrong. Maybe it's a sixth exercise. So it is, if you know calculus, it is not hard. Now I'm doubting. I'm trying to do it in my head, and it's okay. I'm gonna stop there. Okay, so it's easy. I think it's a 6. I think it's gonna work out to a 6. Question mark? Someone check and see if I'm right. So one side is very hard. The other side is it reduces to a simple calculus problem. This is why we learn calculus, so we can do these kinds of things and apply them in real life. Nice connection between your classes. All right, we'll see everybody on Monday. Have a nice weekend. Yeah, have a good weekend.